Good day, dear colleagues. I am Valery Krivogokov from Tomsk Polytechnic University. Let me to continue working of our section. The first report, in white report, stability of zirconium-based metallic glass structure and high temperature plasma impact. Reporter is Dr. Charinda, Nikolai Charinda from Belarus State University, Minsk. Dear Nikolai, you can start, please. Duration of your report is 30 minutes, not more. Please.
Good afternoon or good morning, dear colleagues. First of all, I'd like to thank organizers for a kind invitation to this conference. And now, excuse me, I will switch off the camera just to protect the channel. Okay. This report concerns the stability of metallic glasses under high temperature plasma impact. So I presented on behalf of a large group of authors from Belarusian State University, National Research Tomsk Polytechnical University, Heat and Mass Transfer Institute of the National Academy of Sciences of Belarus, the National Research Nuclear University MFA, and Dalyan University of Technology. So I should mention that these investigations were carried out under the grant of the Russian Foundation for Basic Research. So, a few words about motivation to this work. Some problem, I do not see markers how to change the slides.
I see.
Вот, здесь внизу.
Ага, листовка.
Нет.
I see pointer, but do not see any possible.
Внизу экрана разворачивается такое меню. Вот, и вы можете переключать слайды. Вот внизу, там же, где указка.
Все, я вижу, у меня просто свернут был почему-то.
Да.
Окей.
Let's continue, please.
A few words about motivation of this work. In general, development of new materials that are capable to work under conditions of high temperature, high mechanical load and radiation is still a challenging task for modern material science. In general, metallic glasses possess metastable short-range order structure. So this type of material has relatively good corrosion resistance, relatively high mechanical characteristics. But the most important in our case, that amorphous structured metallic glasses can effectively absorb radiation-induced defects, accelerating materials destruction. In particular, radiation stability of metallic glasses under helium radiation is much higher than that of tungsten. So, metallic glasses can be considered a prospective material that can be used in fusion reactors for optical diagnostic devices, for different geoids inside vacuum chamber, and for some type of reactors, even as first wall material. Different metallic glasses are also prospective material for fuel elements claddings in fission reactors of fourth generation. But the metallic glasses preserve its amorphous structure during heating only up to the glass transition temperature. This temperature depends on the type of material and cooling rate during material synthesis. This temperature, glass transition temperature, is usually about 0.4, 0.6 of base material melting temperature. So it means that heating of metallic glass above this temperature results in the appearance of local crystalline areas or full crystallization, resulting in accumulation of radiation damages and worsening radiation resistance. For example, just here, you can see that X-ray diffraction patterns of zirconium-based foil, and you can see that the heating up to the temperature of 700 degrees resulted in crystallization of the foil. In general, interaction of ion and plasma fluxes with metallic glasses already lead to heating of the material surface layer. In case of pulsed intense ion beams and high temperature plasma flows, the temperature of the target surface layer could be much higher than the melting temperature. Thus, the resulting structure, whether it will be disordered or crystalline, the structure of metallic glass, will be influenced by the cooling rate after ion or plasma flux input. This cooling rate, of course, will be dependent on material type, radiation characteristic. In any case, if the cooling rate after high temperature plasma input will be higher than the critical rate necessary to preserve amorphous structure, then one could expect that the glass structure will be stable under plasma effect. It preserves its disordered structure. For example, earlier conducted investigations showed that treatment of iron-based metallic glass by high-intensity pulsed ion beam didn't change its disordered structure. So, investigation of metallic glass structure stability under high-temperature plasma input and helium ions irradiation were the main aims of this work. The samples of zirconium-based metallic glass were in the form of foil, were produced by quenching from the melt using this type of installation located and developed in Mafia, Moscow. Just here you can see that the two isomorphous elements, zirconium and titanium, form the elemental and structural basis of the foil. The approximate thickness of the foil was 50 micrometers. Well, the compression plasma flows generated by gas discharge magnetoplasma compressors were applied to test this material under material structure stability under plasma input. I will not stop on the physical principles of compression plasma flows generation. These questions were discussed in details at a number of previous conferences in Tomsk. If someone is interested, then this information can be easily found. The treatment parameters are shown on this slide. In general, the heat flux absorbed by the surface layer, I mean the heat flux registered by calorimeter, can reach up to 60 or 70 joules per square centimeters per pulse. In this experiment, the energy absorbed by the surface layer of the target was varied in the range of 4 to 10 joule per square centimeters by changing the distance between the sample and the cathode. Helium implantation was carried out using cyclotron DC-60, located in Kazakhstan, Nur-Sultan, at Eurasian National University. The energy of ions, you can see, was 40 keV, and doses were changed up to 6 multiplied 10 to the power of 17. Well, let us consider investigation results. The first question that appeared was redistribution of elements in the surface layer. This kind of phenomenon was observed earlier in certain materials after plasma input. From this figure, you can see that no changes of elemental composition in the surface layer with the thickness of 1 micrometer was found. And 1 micrometer is simply the thickness of the layer analyzed by energy dispersion X-ray analysis. It should be noted that some contamination of carbon at the surface was found, but it was not, its concentration was not taken into consideration. Well, the X-ray diffraction data showed that foil phase composition after CPF treatment was strongly dependent on the energy density absorbed by the surface layer. For the first, let us consider the initial sample. Two broad diffraction lines corresponding to the structure with a short-range order are observed at the diffraction pattern of the initial foil. The angle position of these two diffraction lines was close to the angle position of low-temperature zirconium and low-temperature titanium standard diffraction lines. So it is known that zirconium and titanium forms a solid solution in the whole concentration range, both for low temperature and high temperature polymorphic modifications, I mean in equilibrium conditions. So one can conclude that zirconium-titanium disordered solid solution on the base of low temperature phase having the hexagonal lattice may be containing copper and nickel atoms as alloying elements was the main phase of the foil produced by quenching from the melt. Lattice parameters that were calculated from diffraction pattern are shown here on the slide. You can see that the values of lattice parameters were aligned between the corresponding values of zirconium and titanium, but the C/A ratio for disordered solid solution, this one, was less than corresponding values for zirconium and titanium. That can be attributed possibly to the influence of alloying elements. Plasma treatment at the largest distance between specimen and electrode that corresponded to energy density of 4 joule per square centimeters didn't change phase composition of the surface layer analyzed by X-ray diffraction. But increase of the energy up to 8 joule per square centimeters led to appearance of crystalline phases inside disordered matrix. Standalone diffraction lines of alpha zirconium and nickel were clearly identified. Besides that, diffraction lines that can be attributed to the zirconium-titanium solid solution were found. The further increase of the absorbed energy up to 10 joule per square centimeters resulted in full crystallization of the surface layer. The presence of the following phases was observed. It both low temperature zirconium and titanium, it's zirconium-titanium solid solution, copper, nickel, and beside that, two polymorphic modification of zirconium oxide were found. It should be noted that intensity of zirconium-titanium diffraction lines was increased, while intensity of zirconium diffraction lines was decreased with the growth of the energy density. According to the data of the phase composition analysis, so zirconium and zirconium-titanium solid solution with possible addition of other alloying elements were the main phase constituent of the analyzed layer after treatment at 10 joules per square centimeters. Just again, lattice parameters of zirconium-titanium solid solution were calculated. You can see it on the slide. The most strange thing appeared that the average C/A ratio was equal to 1.496, so it's much less than zirconium and titanium. It should be noted that C lattice parameters value appeared too small for zirconium lattice and was slightly greater than that of alpha titanium lattice. So it can be explained either by the presence of tensile residual stress inside lattice along C direction, or maybe preferential occupation of atomic inner position in the hexagonal zirconium lattice by titanium atoms. The general appearance of zirconium oxide in the surface layer could be explained by interaction of residual atmospheric gases, in particular oxygen, with atoms of the surface. So as a result of such interaction, surface oxide with a thickness of few tenths of nanometer grew on the surface. Zirconium oxide with monoclinic crystalline lattice is a stable polymorphic modification of zirconium, so it's long temperature phase. Presence of high temperature zirconium oxide with cubic lattice could be connected with its stabilization by other alloying elements. And one more concerning the slide. It should be noted that formation of zirconium nickel or maybe zirconium copper intermetallic phases in the surface layer was also possible after plasma treatment at 10 joule per square centimeters. But the angle position of some intermetallic phases diffraction lines, for example, well-known copper 51 zirconium 14, coincides with angle position of other phases revealed in the analyzed layer. So, I mean, no separate diffraction lines of intermetallic phases with high intensity were found at this diffraction pattern. Well, the results of surface morphology investigation of foils before and after plasma impact are presented just here. So you can see that the increase of the energy absorbed by the surface resulted in the formation of wavy surface relief that is characteristic for crystallized melt after high temperature plasma impact. In general, development of different kinds of hydrodynamic instabilities on the plasma melt border can be the main cause of this effect. For example, well-known Kelvin-Helmholtz instability that formed at the interface between two horizontal parallel streams of different velocities and densities. In our case, it is plasma flow spreading along the surface of the melt. So vortices at the surface of the melt are formed as a result. So they just disturb the surface and can look like waves after crystallization. In general, these effects were simulated by our colleagues from South Ural State University in Chelyabinsk. It's Professor Yelovets and Associate Professor Levy, and wonderful correlation between the data of simulation and surface roughness and wetness was found. And one more point that at this low magnification, the element distribution was found to be homogeneous. So the idea, of course, to check much higher magnification, and the results are shown here on the slide. Here you can see that after plasma treatment at 4 joule per square centimeters, formation of clusters with a maximum size of approximately 500 nanometers was found on the surface. Due to elemental contrast, it's bright areas. Just due to this elemental contrast formed by backscattered electrons, these clusters had higher density, higher atomic density, or contained heavier elements. So one could suppose that these clusters should be zirconium enriched as compared to the metals. Clusters formation just indicated the beginning of disordered structure disintegration, in spite of the fact that crystalline phases absence, the crystalline phases were not found in the diffraction pattern. The further increase of the energy density resulted in cluster size increase up to 2 micrometers. This treatment regime corresponded to appearance of crystalline phases of alpha zirconium, zirconium titanium solid solution, and nickel. At the same time, energy dispersion X-ray analysis didn't reveal changes in elements' homogeneous distribution, just a bit. Besides that, formation of dendrites, small dendrites, and discontinuous surface film was found after increase of the energy up to 10 joule per square centimeters. These effects can be seen more clearly on the next slide. Well, okay. Here you can see small dendritic shape precipitates with the approximate size of 1 micrometer or less. Elemental analysis showed that these precipitates were enriched with titanium. That correlated with the results of phase composition analysis that revealed alpha titanium crystalline phases appearance. Just here, thin oxygen containing discontinuous film can be seen according to the data of the phase composition analysis. This film contained 2 polymorphic modifications of zirconium oxide. Well, you have seen that plasma treatment under used parameters resulted in the crystallization of the foil, at least its surface layer. So the cooling rate of the plasma impact was lower than the critical rate necessary to preserve amorphous structure. Its value should be in the range of 10 power to 4 or 10 power to 6 Kelvin per second. The question appears on the stability of the materials to helium radiation, in particular on the resistance to blisters formation. At the first stage, reaction of the initial foil structure to helium implantation was investigated. Just from this slide, you can see that no changes were found in the diffraction pattern of the foil before and after implantation up to this dose. Similar remark can be made on the surface morphology of the foil. Of course, the question of structural changes visibility is closely connected with used techniques. According to SRIM calculations, the depth of helium ions penetration is just about 400 nanometers. This value is 10 times less than the X-rays penetration depth during X-ray diffraction analysis. So the structural changes may be not seen by this technique if they occur. Of course, using transmission electron microscopy and by analyzing sample cross-section, helium-enriched layers can be seen. For example, just like here, helium-containing layer looks like this bright area at the cross-section of iron-based metallic layers. This layer has higher brightness just at the mean projective range. In our case, the maximum concentration of helium atoms inside the foil can be estimated knowing the approximate atomic density of the film. So this value and this dose is just about 15 atomic percent. So this helium content maybe is not enough to form visible blisters. At the same time, we can stimulate their formation by stimulating diffusion processes. So, at this slide, one can see the surface morphology of implanted foil before and after annealing. Annealing at the temperature of 500 degrees led to surface blisters formation. This one, covered blisters and uncovered blisters. Here they're at high magnification. 500 degrees is a temperature that is lower than the crystallization temperature of the foil. At this temperature, we also do not see any redistribution of elements at the surface. Formation of blisters after annealing generally is indirect evidence of helium presence in the surface layer. Well, helium implantation also carried out into the samples which were previously subjected to plasma treatment. The dose was increased 2 times to enhance implantation effects. At this figure you can see diffraction pattern of foil treated by plasma flow and diffraction pattern of foil treated by plasma flow and implanted by helium ions. In general, there are no significant changes between these two patterns. Some difference in intensity of the diffraction lines was simply caused by orientation of the foil to the X-rays during analysis. So I mean that no sample rotation was used during X-ray diffraction investigation. Surface morphology investigation after plasma treatment and helium implantation show just again developed roughness and waviness that was not differ from the surface morphology before implantation. Following annealing and microscopy investigations do not give adequate information on blisters formation of the sample, treated both by plasma and implanted by helium ions. Just due to developed roughness of the samples after plasma treatment, we do not see blisters here. So we cannot give now the answer to question whether the crystallized structure of the foil possesses worsened resistance to blistering or not. In any case, we are working in this direction. Well, though we're just in time, the conclusion to this work are summarized here on the slide. But in conclusion, I'd like to say the following. The idea that the metallic glass will remain in disordered structure during cooling from the melt after plasma impact with used treatment parameters didn't work in our case. The cooling rate of the plasma impact was much lower than the critical rate necessary to preserve disordered structure. Maybe at lower pulse duration, the cooling rate will be higher, but in any case, surface layer melting under condition of plasma disruption events in different kind of installation, plasma installations, with real duration of milliseconds or higher, will be lead to crystallization of metallic glass. And one more important moment. The structure of the metallic glass, you can see, was strongly dependent on the energy density absorbed by the surface layer. So, compression plasma flows can be used for the testing of such gentle material like metal glasses for the stability, to test its stability under plasma or temperature impact. Why it is important? Because there is no plasma accelerator that can work in all time and energy ranges realized in real installation, like different types of fusion reactors or like ITER. So we just find suitable or proper pair of testing technique and tested material. So thank you very much for your attention. I should
Thanks
take
a
the
lot.
questions maybe.
Thanks a lot, Dr. Cherinda. What about questions? No questions.
Okay, anyone
Very
can ask it later.
report. Let me give you one question, please. What about status of surface? Is it contains the liquid phase or never, only solid phase?
During plasma effect, we receive at lower energy, we see local areas of melting, but very small. So during X-ray analysis, we do not see any crystallization. At higher energy, of course, melting of the surface occurred during plasma impact. So surface layer was melted and crystallized at high energy.
I see, thank you.
Thank
But in this case, it's possible to ask you about what is the reason that main parameter is energy density only? Probably in this situation, a very important parameter is rate of temperature changing, yes?
Of course, but we cannot change now parameters of the pulse, so they are constant. So duration of the pulse is just about full duration, 100 microseconds, and now we cannot change anything here. But we can, of course, we can change or influence the question of changing the temperature in the surface layer, but just changing the distance, for example, or changing the energy of capacitor. But in any case, it will be resulted as integrated characteristic, the energy that was deposited in the surface layer. So it's integrated parameter. But of course, you are right.
Thanks a lot. Thanks a lot.
Thank you.
More questions? No? Thank you, Dr. Nikolai Cherinda. Thank you. Next report is spatial temporal distribution of parameters in the plasma layer formed by surface evaporation with high brightness red band short wave radiation. Dr. Alexey Pavlov, please. Your duration is not more than 20 minutes. Questions? With questions. Please, Dr. Alexey Pavlov.
You hear me? Hello? I hear me? What is the sound? Okay, thank you very much. I need to switch off my camera due to connection lag. Participant. I'm Alexey Pavlov, and I will speak instead of Victor Telech. And we see the distribution of plasma parameters along the targets belong the our excuse me. We say distribution of plasma parameters in the layer of vapor plasma above target under the powerful wideband high brightness radiation in the vacuum condition, and this research actual in such application as wolf lithography, space materials design, and other applications. We use MPC discharge, such a source of vacuum radiation. We choose this source as more suitable for our targets. Its spectral intensity distribution lays in the vacuum area, and the focus creating near the central electrode is a source of power wideband radiation. We placed the targets from different metals above the targets, above the discharge, and we have a Teflon target as evidence bottom of charge, and we use it for control quality and quantity of irradiation falling on the target. And also the position, the specific position related to a MPC device allows us to see different effects on the surface of targets along because the near and far side of the targets is taking the different intensity from MPC discharge. Our discharge cell consists of is very simple and consists of capacitor, teratron for connection, and MPC device consists of two coaxial electrodes with Teflon insulator. And then insulator is a source of plasma for focus creating in the vacuum of camera. We use inert gas such as neon, argon, and xenon. We use the optical diagnostic of our processes. This setup described in previous article, and if we say some words about it, we have a universal diagnostic installation, including direct Dopplerograms and shadow graph, and double exposure holographic interference for diagnostic of refraction ratio of vapor plasma flows from our targets. We use the nanosecond second harmonic neodymium laser, and we synchronize the impulse of our diagnostic laser with the beginning of discharge. There's a we can see the result of different diagnostics, such as direct the direct diagnostic allows us to see the glowing vapors above the Teflon target, and we don't see the vapors above metallic targets. But the inside structure of the targets we see on the next diagnostic, such as Dopplerogram shadow diagnostic. We see the character effects, type of effects above the targets in the vapor plasma layer and near the targets. There is plasma vapor contact boundary above between vapor plasma layer and shock compressed gas, and the shock wave between the shock compressed gas and background gas. And the Teflon evidencer allows us to exactly see such effects, but on the metallic, such effects on the metallic target not so clearly. We see the moment of on the oscillogram. We see a moment of laser impulse from the beginning of the discharge, and also we see the distribution of light intensity of our discharge. and the next diagnostic double exposure holographic interferometry allows us to follow the path interference layer path shifting, and these shifts allows us to determine the plasma parameters by the changing of refraction index, refraction ratio in the characteristic fields. We perform our experiment on the voltage of 20 kilovolts, and these shoots were made at 10 microseconds from the beginning. Also, we can see the three types of disturbances of the background gas along the target, along the surface of targets. On the far side, we can see the acoustic wave, the next the simple wave, and third disturbance is a shock wave, and and next we we will see at the third types of our effects. From the interferograms, we see the energy distribution on the target. The falling radiation goes to heat conductivity, reflection, shock, compressed gas generation, and absorption of in target plasma for heating and further transmitting. And taking in mind that some energy absorbed in the compressed gas is kinetic energy, and inner energy if we see on the interferograms, we can estimate the some energy in the plasma layer. The ratio of height between shock wave and the target and contact boundary and target allows us try to estimate that the density ratio is about 2, and if we calculate the energy, calculate the Gugonian, and then calculate the energy, we determine that sum energy is about 0.08 joule per square centimeters. And I want to note for the path of interference lanes. We in AB, this is the interference lanes number 20, 21, 22, 23, and the dotted dashed line we V is a vacuum lane for the lane number 20 with absolute refractive index calculated in this example. The delta K minimum F is minus 0.4. If we look at the sections of lanes, we see not disturbed background gas in AB section, shockwave area at BC section, and density considered density jump. We have no significant slope on the CD section, which means that the density does not change in height in the compressed gas. And other section DE, this is a contact boundary between phase change, phase of vapor plasma and compressed background gas, and following the lane, we see the DEFGH path is a changing of parameter vapor plasma substance on the at the height of layer. Take in mind previous determination, we try to determine the changing of pressure in the height at the height of our vapor plasma layer, and this is accelerating expanding vapors, and if we calculate the thickness of unformal changing, we have that on the 5 millimeters of height of our layer, we have a homogeneous atmosphere is 1 centimeter, and thus the pressure drop in this vapor layer is no more than 2. Okay, we can imagine that previous determination in the as the curve on the CEP diagram, we see lines of equal concentration and lines of equal reference index. From these diagrams was calculated from third code of thermodynamic, optic, and transport properties of plasma, verificated code, and if we draw a line of equal concentration and considering a line of constant refractive index, and place the points calculated on previous steps, we can determine other plasma parameters such as temperature, concentration, and other parameters. And for these curve was drawn from the 20 number lane, interference lane, and for other lane we will have other curve, and for other materials we will have other curve. It is a goal of our next researchers. And for band number 50, we get some result, and the dot code calculate the enthalpy for these parameters, and knowing heat of vapors above the targets is about 4 millimeters, and the density we determine the vapors mass per unit area. When the energy in vapor per unit area is about 5 joule per square centimeter, and if we sum it with phase transition and energy in the shock compressed background gas, we obtain 5 near the 5 joule by square centimeter. And the main conclusion of our research is determination of energy falling on the targets, and if we take in mind our discharge parameters and energetic parameters to 10 microseconds from beginning of the discharge, we have 5 joule per square centimeter, and that's near the NPCH of the targets. And if the think that the luminous flux increase linearly of our 8 microseconds, when the maximum power is about 1 or 1.5 megawatts per square centimeter. Thank you very much for attention.
Thanks a lot. Thanks a lot. What about the questions? I don't see no questions. I have one question for you. Please, what is your opinion about the reflection of energy from surface of your target? Reflection of it.
We have the Teflon targets reflects less energy in compare with metal targets, and the quality of the surface and the roughness of the surface on metallic targets is do reflectance more or less if the roughness more or less than the polished surface of metal targets. But we have Teflon targets as the evidencer of quantity of energy, and its reflectance not so high than metallic targets. Okay.
I see. Next report: influence of the arch magnetic field in the cathode erosion rate of the vacuum arc discharge. by Daniil Kirillov, Bauman, Moscow State Technical University. Please, 20 minutes. Question.
Okay, thank you. Do you hear me?
Yes, excellent.
Okay, thank you very much. I hope you see the pointer on your screen. Our work was done in Bauman Moscow State Technical University in Science and Educational Center of Ion Plasma Technology. This work is dedicated the investigation of vacuum arc characteristics in arc-light magnetic field. The vacuum arc widely uses in technology, for example, for wear-resistant and hard-resistant coatings, for anti-friction coatings, heat-resistant coatings in production of war aircrafts, for medical tools, teeth and joint implants coatings, and as you know, in decorative coatings with titanium nitride or zirconium nitride coatings. So the main parameters of each technological tool is its productivity, and for vacuum arc operators it is erosion rate. The erosion rate characterized by mass change of the cathode divided to arc current at time and time. And erosion rate consists of at first ion flow, ion mass flow, neutral atoms mass flow, and also microparticles. As you know, microparticles is the main disadvantage of this method. This flow goes from the cathode sport crater area. So here you can see cathode crater, and the cathode craters with diameter of about for titanium 70 micrometers. This crater consists of large amount of little craters with diameter of from 2 to 10 micrometers. And from this area, the ions and microparticles go towards to vacuum volume. Usually erosion rate considered as a constant, and the erosion rate was calculated experimentally, mainly experimentally, for different metals. But I should note that these numbers was obtained only for cathodes, only for evaporators without magnetic field or with magnetic field of actual shape. But there is a number of evaporators of our construction or foreign construction, which is widely used magnetic field to control cathodic sport movement. But the main goal of this work is to investigate the magnetic field influence on characteristics of vacuum arc evaporators, such erosion rate. The work was done only on industrial cathodic arc evaporator. This was produced, developed by our team, and this consists of taper flat cathode with diameter of 150 millimeters. Here you can see a node flange, neutral insert, magnetic field system consists of main magnet coil and additional magnet coil, coolant system, ignition system, and with the magnet system, the arch-like magnetic field applied to the surface of the cathode. This field is like on magnetron pattern system. And the cathode spot moving quickly on the center of the the arc of magnetic field. The next, here you can see the vacuum chamber. This is a setup of UVN74. Here you can see cathodic arc evaporators and this picture with substrate. So here you can see the magnetic field shape, magnetic field characteristics, and these pictures you can compare the magnetic field without, cathode spot movement without magnetic field and cathode spot movement in arch-like magnetic field. And here the beautiful picture of continuous movement cathode spot with dynamic magnetic field changing. So the next, at first, I should note that at magnetic field, the velocity of the cathode spot is increased. The work was done, I should note, for titanium, copper, aluminium, and silica. For all of these materials, and I think for all materials we can investigate. For all the materials, the velocity increases with increasing of magnetic field. You can see this as the length of the cathode spot track. The next, the erosion rate was measured with the direct weighting of the cathode before and after experiment. This work was done for different materials, I said, and with a different magnetic field. So as you can see, the erosion rate is not constant for all of the materials we considered, and also I think for all of the materials which can be used for this technology. The erosion rate decreased with increasing the magnetic field. You can see this for titanium or for copper and for other materials. And the erosion rate reducing degree is drastically for titanium. Here you can see the erosion rate decreases up to 4 times with increasing the magnetic field from 0 to 12 millitesla. For another materials, the erosion rate reduction isn't so drastically. So, and from this data, we can conclude that the optimal magnetic field we made to use for industry vacuum arc evaporators is from 3 to 8 or maybe 10 millitesla. With this area at 3 millitesla, cathode spot is already controlled, fully controlled, and with this area 8 or maybe 10 millitesla, cathode spot is fully controlled, but erosion rate reduction is not so drastically. The next, what's the origin of this decreasing? Let's discuss it. At first, let's look what's the erosion rate one else. Erosion rate consists of ion mass, ion flow rate, neutral atoms flow rate, and macroparticles flow rate. Neutral flow rate is very small. It's about several percents So we can observe only ions or macroparticles mass loss. So the ion mass flux to surface can be calculated from the very thin coatings. The thickness of these coatings is about 70 nanometers. So here you can see this picture obtained on atomic force microscope, or maybe profiler. Here you can see substrate and these coatings, which consist of flat areas, which is only iron coatings, and these peaks, it is macroparticles. So when we measure thickness of the coatings without macroparticles, we can conclude the ion mass flux to the surface. So the next we can calculate, we can estimate mass flux from the macroparticles. So we can know the macroparticles form. The macroparticles form is like a disk or maybe head, and we can calculate the shape parameters such as aspect ratio is height divided to diameter. And when we obtain this shape characteristic, this is a difference from the magnetic field, and with known size distributions of microparticles, we can obtain mass of microparticles mass flux from the magnetic field. At this picture, you can compare the two pictures from ion mass flux and macroparticles mass flux reduction from the magnetic field. And this table, I place the numbers may help you to compare these pictures. As you can see, the ion mass flux reduction from ion flux is not so drastically decreases that in macroparticles flux. So we can conclude that erosion rate decreases is mainly from macroparticles flux decreasing. So the main conclusion I may to say you is that the erosion rate is maybe drastically depends on the induction of arched magnetic fields for different materials. And this is due to two factors. The first, the decrease of ion component, and the second, the decrease of macroparticles flux. And the main roles plays is just the macroparticles flux. And the important conclusion is that the optical magnetic field for industrial arc operators is 3 to 8 or 10 millitesla. So that's all. The one thing I want to know that this work was done under leadership of our director of our center, which is unfortunately was gone in 10th of April by COVID. This is our head of the Hopelnikov Dmitry Vladimirovich. Thank you very much. Please, if you have any questions, feel free. I'll answer you. Any questions?
Please, your questions, dear colleagues. I have one question, Daniil. What you can say about the atmosphere inside of your vacuum chamber? I'm talking about the contents and pressure.
Oh, sorry, I didn't say it. The experiment was done, and the technology is in vacuum with the pressure of 10 in minus 4 or to minus 6 millitorr. And maybe the atmosphere will be with argon.
I see. Thank you. More questions?
Okay, I see two questions. May I answer? First, Ilya Lopatin, have you tried use graphite as a cathode materials? Does the design allow to avoid appearance of deep craters on it? Yes, we tried the graphite. Sorry, we tried this. There is some of thin things with it, but we obtained the diamond-like coatings with this. We had big craters, but with some of parameters of our evaporator, the craters was not so big, and the cathode spot movement very quickly on the surface. So, Olga Krisina, may I ask on Russian? Answer, sorry, Russian. Вместе с уменьшением потока макрочастиц ионного потока изменяется и скорость роста покрытий. Прокомментируйте как. Скорость роста покрытий изменяется пропорционально уменьшению скорости эрозии. Но при этом в основном, как я сказал, за счет капель. То есть, грубо говоря, у нас производительность уменьшается, но при этом у нас улучшается качество самого покрытия.
Thank you. Еще один вопрос, one more question.
Yes. Как повлияло уменьшение капель на свойства покрытий? К сожалению, мы еще не проверяли влияние на механические свойства покрытия, но я полагаю, что, во-первых, у нас твердость покрытий как минимум уменьшаться не будет. Может быть только улучшение свойств покрытий в связи с уменьшением количества капель, количества дефектов. Вот. И это мое заключение обусловлено тем, что параметры плазмы практически не меняются. Единственное, что меняется, это увеличенный нагрев плазмы в замагниченной области, в области прикатодной, где есть арочное магнитное поле. Но и то оно не столь существенно для тех магнитных полей, о которых мы сейчас говорим.
Thank you, Daniil.
Thank you very much.
Very good report. Thank you. So I would like to inform you